go ahead and introduce our speaker for tonight. So our speaker tonight is Shen. Ken's research is on interacting binary star systems with a focus on thermonuclear transient events. Ken grew up in the Bay Area, got his PhD at UC Santa Barbara in 2010, and has been doing research at Berkeley ever since. Title of the talk tonight is Hypervelocity Messengers and the Origin of Cosmic Explosions. So without further ado, I'll hand it over to Ken and enjoy the talk.
All right. Thank you all so much for coming. How's the volume? There's no feedback. Oh, okay. Stephen says it's okay. Great. So yeah, thank you all very much for coming. You all have the honor of being my first audience for a real Zoom talk. So hopefully no technological pitfalls will get us. One benefit of giving a talk from home is that my dog can hear. So there's my dog. I'm gonna quiz her later on what she learned, but I don't have high hopes because she is only 1.5 years old, so she's probably not gonna be able to retain the subject matter. Okay, so what I want to tell you today about is supernovae. So these are explosions of stars. In particular, I want to talk about how the discovery of very, very fast stars has confirmed our model for what causes these explosions. Now, supernovae, again, they're the deaths of stars, and they occur roughly once per every century or so in the Milky Way. They're very, very bright, though, so we can see them in other galaxies. And as a result, we see lots of them throughout the year. So this, this visualization is going to show you all the supernovae that we were able to detect and observe as a community in the early 2010s. So here they go. There's something like a few hundred-ish or a bit more per year. These days, as telescope technology has gotten better and surveys have been designed to find more and more supernovae, we're discovering more like 1,000 or even several thousand per year. And in the coming years, as we ramp up the Vera Rubin Observatory, we're going to be observing something like tens of thousands or even hundreds of thousands of supernovae per year. So they're somewhat common throughout our universe. Now, supernovae come in two main classes, core collapse supernovae and type 1a supernovae. Core collapse supernovae, otherwise known as type 2 or type 1b or type 1c, these are due to the deaths of massive stars. So stars that are 10 or 20 or 30 times the mass of the sun, when they die, they collapse and they explode. Okay, and these are very, very interesting things, but I don't know that much about them, so I'm not going to talk that much about them today. My research focus is on type 1a supernovae. And in words, these are the thermonuclear explosions of white dwarfs. Now, I'm going to give you some more detail on what these words mean in the next coming slides, but suffice it to say, these are basically giant bombs in space. They're cosmic bombs. So they're runaway thermonuclear fusion events inside of stars that lead to their deaths. What does the type 1a supernova look like? Well, this is actual data or images from a recent supernova that happened in the year 2011. So this is an image of the Pinwheel galaxy, and you're going to see over the course of weeks to months a supernova happen. So there it goes. It gets brighter over something like a few weeks, and then it fades over another few months. You can see the time down here. If you were to take the light from that supernova and make a plot of it, so what's called a light curve, it would look something like this. So this is a plot showing how bright a supernova is, how bright a type 1a supernova is, versus the time that it's been evolving for. Okay, so this is in days from the maximum of its luminosity. So in roughly 20 days, it gets brighter and brighter. And then after another 20, 30, 40, 50, 60, et cetera, a few months, it gets fainter and eventually fades away. Now, something really, really interesting about type 1a supernovae is that the light curves of different kinds of type 1a supernovae all look pretty similar. There's some details that go into how similar they look, but at least at a very basic level, they all look very similar. And that's really important because in astronomy, it turns out to be really hard to discover or to find out how far away things are. Okay, on Earth, this is obviously really easy. You know, just take a ruler or whatever, but in space, it's not so easy. You don't have rulers all over the place. And so it's not always it's not always easy to find out how far away a different galaxy is, especially the further away the galaxy is. So type 1a supernovae are great because they are basically what are known as standard candles. They all reach roughly the same luminosity. And since something that's further away appears to be dimmer, we can say when you see a type 1a supernova in another galaxy, based on how dim it appears to be, we know it's actually this bright. And so we know how far away that galaxy is. And with that information and some other information, people were able to discover that different further away parts of the galaxy, further away parts of the universe are actually expanding away from us faster and faster, and what's known as cosmic expansion and cosmic acceleration. And I don't have time to get into the details because that would be a whole nother talk. But this was the basis for the discovery of dark energy, that there's something in the universe, roughly 3/4 of the universe, that is causing space itself to expand away from itself faster and faster. And the use of type 1a supernovae to, as these cosmological distance indicators led to the 2011 Nobel Prize in Physics. Much of this work was done at Berkeley through Saul Perlmutter's group at Lawrence Berkeley Lab, as well as in Alex Filipenko's group on campus. Okay, so this is probably the main reason why non-astronomers would have heard about type 1a supernovae in the news, as their use as cosmological distance indicators and this Nobel Prize. But while cosmic acceleration is extremely interesting, it doesn't really affect us in a day-to-day way here on Earth. But type 1a supernovae are still important for our day-to-day life. So this is a periodic table. Hopefully you remember this from high school chemistry or whatever. The heavier elements, the lighter elements are up here, and it gets heavier as you go down the table. What this periodic table shows is the contribution of different processes in astronomy to the production of these elements. So we all know the famous Carl Sagan quote, we are all, basically we're all made of stardust, star stuff, and that's shown in this periodic table. What we want to focus on is this light blue region, which is being produced by type 1a supernovae. So they explode and they spread that thermonuclear ash throughout the galaxy to form new stars out of. So when new stars form and new planets form, they're forming out of stuff that has potentially been enriched by all these events, including type 1a supernovae. And we see that these light blue regions are prominent in, say, silicon, roughly half of the silicon and half of the sulfur, half of the calcium, and the majority of things like chromium and manganese and iron and cobalt and nickel come from type 1a supernovae. So they exploded a long time ago, they spread their ashes throughout the galaxy, and then new stars and planets form from those, and that's what leads to the enrichment we see here on Earth. Now these elements are very important, obviously. For example, all the steel that goes into buildings and bridges, the iron that's in that steel is mostly coming from type 1a supernovae. The iron and the chromium and the nickel that goes into your stainless steel cookware is coming from type 1a supernovae. And very importantly for life, the iron at the center of hemoglobin is mostly coming from type 1a supernovae. So that's one reason why you might care about type 1a supernovae. But I personally, I don't study them because of what they do for us. I study them because they're really interesting, right? They're, again, basically giant explosions in space. And I think it'd be really useful to know how and why they occur. And so over the next 40 minutes or so, I'm going to be telling you what we know about them and what the model I've been working on, how that works, and why I think that we are well on our way to understanding how these explosions happen. Okay, so let's return to what's known as this light curve. So again, this is how bright a supernova gets as a function of time. And as I said before, type 1a supernovae take roughly a few weeks to get bright and then a few more weeks to start to fade. Okay, and that seems like a pretty basic piece of knowledge, but it actually tells us a lot about what is leading to type 1a supernovae. And the reason that this is because it takes light a finite amount of time to get through stuff. Okay, so there's some amount of stuff inside of the ejecta that leads to the supernova. And the fact that it takes a few weeks to get bright and to fade tells us roughly how much stuff there is. Right, so what I'm trying to say is that light doesn't just immediately come to us through material. It has to bounce around. So say there's an atom here, the light's coming, and it gets absorbed by that atom. And then the atom re-emits it or does something to it, and it scatters it into a different direction. So now it goes off here. And this goes on and on and on until finally that light is able to get off this edge of the screen and come to us with our telescope. So the amount of time it takes the light to get out of this material tells us roughly how much material there is. And from the fact it takes a few weeks, it tells us that a type 1a supernova has roughly the mass of the sun inside of it. So that's a pretty rough number. It could be maybe a half a solar mass or 2 solar masses, but it's not 10 solar masses. It's not 100 solar masses, right? It's not a lot of mass. And so that tells us that it's not the collapse or the explosion of a very massive star. It's instead something roughly the mass of a typical star like the sun. Okay, so that's what happens if you just collect the light coming from the supernova through a telescope. But we can do a little better. We can pass that light. Basically, we can pass that light through a prism, a fancier prism, but basically a prism. And what that does is it refracts light into different directions based on the wavelength. So we've probably all played with prisms back in elementary school, and we saw that red light gets refracted less than the bluer light. Okay, so if you take this white light, it will separate the light into its different wavelengths, and if you place a detector over here, you can measure how bright the red light is versus how bright the green versus how bright the blue. Okay. And if you do that for a star like the sun, you get what's called a spectrum that looks something like this. And what you can immediately see is that it's not continuous, right? There are these gaps in the light, gaps in the spectrum that we call absorption lines or absorption features, because the light on its way to us has been absorbed by something, right? So this light here didn't make it to us, and that's why it's dark. We don't get that reddish light at that particular wavelength. And that tells us something really, really important about the composition of the star or the composition of the supernova. That has to do with, due to quantum mechanics. So what quantum mechanics tells us, or one of the things that it tells us, is that energy comes in very discrete bundles. Okay, it takes a specific amount of energy to change. For example, it takes a specific amount of energy to change the energy level of an atom. So in this example, I have a proton with an electron attached to it. So this is just a hydrogen atom. And in this particular example, the electron is in a certain energy state. To transfer it to this other energy state takes a specific amount of energy. Okay, so light carries energy. The red light, which has less energy than is necessary to make that transition happen, just passes on by this hydrogen atom. It doesn't get absorbed, doesn't interact with it because it has too little energy to change the energy level of this electron. The blue light, which has a higher energy, more energy, a shorter wavelength, is too high energy to change the energy level of this electron. You need this green wavelength, this Goldilocks sort of energy that actually is able to change the energy of this atom and get absorbed. And so if I were over here with my detector, the red light would pass to me fine, the blue light would pass to me fine, but the green light would be absorbed and would not appear when I try to measure it, right? So if I make a plot of how bright the light is that's coming to me, the blue light would get to me, the red light would get to me, but the green light, because it gets absorbed by this atom, doesn't get to me. And so I would see a dip here because that green light isn't getting to me. Okay, so this is the basis for a spectrum and what it can tell us. It can tell us exactly what is inside the star or supernova based on these absorption features. So here's the sun. All these absorption features are different elements inside the surface of the sun. So I'm not exactly sure because this spectrum didn't come with numbers, but I think these two lines here are sodium. Okay, so we know that there's sodium in the sun. A bunch of these lines are hydrogen, which makes sense. There's a lot of hydrogen in the sun. There are lines for calcium and iron, et cetera, et cetera. A little interesting historical side note, helium was actually discovered first in the sun. That's why it's called helium, for Helios, the Greek sun god, right? It was first seen as these lines in the sun that didn't have a terrestrial analog. All the other lines in the sun, we were able to match, people were able to match to spectra on Earth. When they took, say, hydrogen gas and they passed light through it, it got absorbed at very specific wavelengths that they could match to lines in the sun. But there were these other lines that they couldn't match and that they called helium. And so helium was actually first discovered via a solar spectrum. Okay, so that's the sun. We can play the same game for type 1a supernovae. So what do their spectra look like? And this is what they look like. So again, this is how bright the light from the supernova is versus the wavelength of that light. And we see these very distinct features. I'm sorry, this is 5 different type 1a supernovae. just showing you that by and large, they look pretty similar to each other. We see this very strong absorption feature here, which is due to the absorption by silicon atoms. So there's definitely silicon inside type 1a supernovae. The same silicon that ends up in your computer is showing up in the spectrum of a type 1a supernova. We also see lines for calcium. So here's calcium. So there's definitely calcium in type 1a supernovae. We see lines for sulfur and iron and a bunch of other stuff. What we don't see is any evidence of hydrogen or helium. So hydrogen and helium make up the vast majority of the material in the universe. So it's really interesting immediately that type 1a supernovae don't show any sign of hydrogen or helium. Okay, if it were there, it would lead to some sort of absorption features, right? But we don't see those. So we know that whatever is exploding doesn't have hydrogen, it doesn't have helium, and it made a lot of silicon and sulfur and calcium, et cetera. Okay, so we can use the spectra to tell us what's inside and what's not inside the type 1a supernova. And the light curve tells us something about how much material is inside the supernova. So that's already some pretty useful information. Whatever it exploded had to produce these particular elements, and whatever it was made of could only be roughly the size, the mass of the sun. I think I'm going to stop there. Well, I guess I'll do one more slide. And so from decades of modeling, what we've come to understand is that the way you get this particular mix of material is to take carbon and oxygen nuclei, have them undergo rapid fusion, so stick together and release energy and transmute into different elements further along the periodic table. And when you do that, you produce the right mix of stuff. You produce a lot of silicon and sulfur and calcium and iron and nickel, et cetera. And that material is what we see in the type 1a supernova. So the basic model that we are working with in the supernova community is to find something that's made of carbon and oxygen and has roughly the mass of the sun and explode it. And if we do that, the result should look like a type 1a supernova. Okay, I'm gonna stop there and take any questions if there are any. How do I do that? Maybe I'll stop sharing.
I can also read them out if you want, Ken.
Yeah.
Okay. So a question from Nick. If you were on a planet in the same system as a type 1a supernova and somehow managed to survive, how fast would the explosion happen in front of your eyes? Would it also take about 60 days, as the luminosity chart showed?
Interesting question. If you manage to survive, that's really the key there, right? The light curves that I'm showing are a measurement of the total energy per second that's coming. And so that's what you would see. It would be that fast. So, it would take however many weeks to rise to its maximum and then get dimmer over however many months. Perhaps the more interesting question is what happens if you don't just become invincible. I think you'd be fried pretty much. I don't, if there's a planet in the system, I think it will definitely be destroyed.
So the next question is from Tamara Saunders. This might be a super existential question, partially related to supernovae, but referring to the periodic table slide, if hydrogen, helium, et cetera, are building blocks to Big Bang fusion, thus planet creation and all that, what creates the hydrogen and helium, or where did it come from?
That's very existential. Well, the hydrogen and helium, so maybe I'll go back to sharing. Share screen, share. Okay. So in the periodic table, Big Bang fusion is this dark blue, and it's showing up in hydrogen and helium and a tiny bit of lithium. And what that's referring to is these things, okay. Well, when the universe was created way back in the day, it was very, very hot and very, very dense, and there weren't really atoms yet. Boy, this is getting into a field that makes me nervous because I don't know anything about it. But very, very basic level, as that material expanded and cooled, you were able to form nuclei and atoms. And the only things that really came out of that Big Bang are these Big Bang fusion elements, so hydrogen, helium, and lithium. Everything else comes from something else. So basically things having to do with stars. But the main building blocks, the hydrogen and helium, are coming from the Big Bang itself. I'm not sure if that, hopefully that answered the question, maybe.
And then one last question from Lee Martin. How does the hydrogen and helium, even on the surface of the star, get fused? I would have thought that the pressures on the surface would be too low, assuming that the absence of hydrogen and helium in the spectrum is because all of it fused to heavier elements.
Great question. So in the next slide, I will try to talk a little bit about how white dwarfs are formed, but very quickly on this, it's a combination. So the hydrogen and helium do fuse into carbon and oxygen, but some of it also gets sort of blown away over a long time scale prior to the formation of a white dwarf. But I will try to answer this in the next slide. Okay, any more questions? Doesn't look like it. All right, so I will move on, and then there'll also be time for questions at the end. Am I still sharing?
No.
I know how to do that. Share. Okay, where were we? Right, so the question is, how do you get all this carbon and oxygen together, and how do you fuse it? The first answer, how do you get all the carbon and oxygen together, is you form a white dwarf. Okay, so what is a white dwarf? Well, in this slide, I'm going to try to explain all of stellar evolution. That I will not do so very well. I highly encourage you to learn more about it on Wikipedia and the internet if you don't already know, but this is a very interesting subject and is the subject of many fields of astrophysics, but I'll try my best in one slide. Okay, so most stars in the universe in our galaxy are what are known as main sequence stars. So stars like the sun that are mostly made of hydrogen. And at the center of the star, at the center of a main sequence star, the hydrogen is being fused into helium. So you take 4 hydrogens and you squish them together and you form a helium nucleus. Okay, and that's what's powering the sun right now. It's what's emitting all that light and what is allowing for life on Earth. Now, there is a lot of hydrogen in the sun, but it's not infinite, and there is a finite amount. And at some point, that hydrogen in the center will all be converted into helium. So you can't do any more hydrogen fusion in the center. You've constructed this helium ball. However, that helium ball will eventually get hot and dense enough to do its own nuclear fusion. And when you fuse heliums, you stick 3 heliums together or 4 heliums together, you produce carbon and oxygen. And so our sun will eventually, after hundreds of millions or billions of years, a few billions of years, will convert the hydrogen into helium and the helium into carbon and oxygen. Some stars are able to continue fusing things. They'll fuse the carbon and oxygen, but our sun and many stars of roughly its mass will not ever fuse the carbon and oxygen into heavier elements. And so the center of the sun and stars like it will eventually become carbon and oxygen. Roughly half, something like that, 60% of the sun will become this carbon and oxygen ball. The rest of the hydrogen and helium on top will be sort of fluffed away through very strong winds, what are known as winds. And so those winds take away the rest of the material, and what you're left with is a ball of carbon and oxygen, and that's what's known as a white dwarf. So it has roughly the mass of the sun, or half the mass of the sun, but by this point it's shrunk down to a very, very small size. So instead of the size of the sun, it's actually more like the size of the Earth. Roughly the mass of the sun and the size of the Earth. It's extremely dense. Okay, so it's a very, very dense object known as a white dwarf. That in the case of our sun will be primarily made of carbon and oxygen. And this sounds like sort of an exotic evolutionary pathway, but this is actually what most stars in the universe will do. They'll form white dwarfs. They're currently burning hydrogen, but eventually they'll form white dwarfs. Something like 90% of stars will do this. And most of them will eventually just fade away and cool for eternity. Okay, so the sun will form a white dwarf in 5 billion years or so, and eventually just cool. However, as I said before, this is perfect. It's a carbon and oxygen ball that's roughly the size of the sun and the mass of the sun. This is perfect for a type 1a supernova, right? But I've also just said that the sun is going to just cool for eternity and not do anything that exciting. If you're into explosions, it's not going to do anything that exciting. What it turns out you need is something to set off the explosion. So you need another star. Now, while the sun is a single star and there isn't another star in the orbit around it, it turns out that actually it's pretty common for stars to have companions either one companion in this GIF of two stars spiraling around each other, or multiple star systems. There are triple star systems, quadruples, quintuples. I actually don't know what the record is. Maybe I should have looked that up before I gave this talk. But anyway, what we'll be interested in here are stars where, systems where there's two stars, and in particular where both stars are white dwarfs. Okay, so you have two white dwarfs in a very close orbit spiraling around each other like this. For some of these systems, they eventually evolve to the point where one white dwarf starts to interact with another white dwarf. Okay, so what this simulation will show is that kind of interaction, where one white dwarf, here's one white dwarf, will be pulling material off of this other white dwarf. All right, so these are two panels of a movie. On the left, we're seeing the density. So where it's brighter, there's more mass. So here's the one white dwarf and here's another white dwarf. On the right, we'll see the temperature. Right now, everything's cold, but when things get hotter, we'll see some stuff happening. Okay, so I'll start the simulation. I will try to start the simulation. Okay, I did. All right, so the two stars are in orbit around each other. One white dwarf is pulling material off of the other white dwarf. And you can see over in this temperature panel that when the material hits the surface of the white dwarf, it gets hot, right? It's colorful here, which is where the material is impacting the other white dwarf. So simulation goes for a while. They're in orbit around each other, more and more material. It's getting hotter and hotter. Eventually, something exciting happens. Okay, and you can see that exciting thing where it gets really bright. This really bright part of the simulation is an explosion. So there's an explosion that's starting to take place on the surface of this white dwarf that has all this material being dumped on it. And the explosion travels around the surface of the white dwarf, makes it all the way around the surface, and then there's a second explosion, right? So you can see that explosion that totally consumes this white dwarf that was getting the material dumped on it, right? So there goes the explosion on the surface, and then sometime later, there's an explosion in the center. Okay, so two explosions, one on the surface and one in the center. Now, I want to be careful with my language because here on Earth, when we say words like deflagration and detonation and explosion, we use them in sort of a colloquial way. But in combustion physics, they have very, very specific meanings. Okay, so what we saw in that simulation were what we call detonations, which is a very specific kind of explosion, a very specific kind of flame and a burning front. This movie will show the difference between the two. So it starts out with a deflagration, so D-E-F-L-A-G-R-A-T-I-O-N, deflagration, which is a relatively slow flame that's moving slower than the speed of sound. So what does that look like? This is a simulation of a deflagration in a pipe, moving down the pipe. Here you see it going. They're characterized by being very turbulent, very wrinkled. And this is the kind of flame that we're used to here on Earth. So when you think about explosions in movies, that kind of stuff, they look sort of like this, right? Kind of wrinkled and yeah. However, at some point, this deflagration is speeding up. It will transition in the simulation into a detonation, which is a supersonic flame. So something moving faster than the speed of sound. You can see it qualitatively changes the character. It's much less wrinkled. It's moving faster. And that is the kind of explosion that happens in this simulation. So in the simulation, we see a detonation wrapping around the surface on both sides. And that detonation on the surface leads to a detonation in the core. Yeah, so there are two detonations. This is what's known as a double detonation mechanism for igniting a type 1e supernova. Okay, so this is how you explode in this scenario that I and others have been working on. Here's a zoom in on the exploding white dwarf. So now this calculation is neglecting the presence of that other star. Here we're just focusing on the star that blows up. And here, this is a cutaway through the white dwarf. So you can imagine this is the North Pole down to the equator, and here's the South Pole, and here's the center. Okay, so this were Earth, here's the North Pole, here's the equator. This would be, the hot iron core, liquid magma kind of thing at the center of the Earth, and here's the South Pole. And in the simulation, we're going to have a surface detonation, so a supersonic explosion traveling around. Here it goes. Oh, sorry, I forgot to tell you what you're looking at. So the colors are temperatures. So blue is cold, red is hot. This is an explosion, so it's hot here. These different white lines, white and gray lines, are contours of density. So you can think of it very analogously to a topographic map, so which would show height. Here, this is showing lines of constant density. It's a white dwarf, and so it's very spherical. So these lines are circles in this cutaway. Okay, but we'll see something interesting happen as the detonation goes around the surface of the white dwarf. All right, so now it's moving down to the equator, still traveling, spreading around the surface. But you can see that there's this kink in the density contours. And this kink is a shock wave. Right, so this is a supersonic detonation. It's moving faster than the speed of sound. And as it travels around the surface, burning, it sends a supersonic shock wave into the core. Okay, there it goes. It's traveling all the way. If this were Earth, it'd be going through Australia, roughly. Here it's hitting Antarctica or something like that. And now it's made it to the South Pole. Okay, so the detonation has traveled all the way around the surface, but the shock wave that it's sent into the core is still going. Still going, and as it's going, it's focusing its energy into a smaller and smaller volume, right? It started out way over here, and now all that energy is being focused into a little volume here. And when you focus a lot of energy into a small space, the temperature can get high enough to initiate the fusion of the carbon and oxygen at the center of this white dwarf. So that's what happens in the simulation. All the energy gets focused, and it starts this second supersonic detonation that then explodes the rest of the white dwarf. All right, so let's just see that again. Here goes the surface layer detonation. You can see that shock wave converging, and eventually, once it all focuses, it's coming, it sets off a second explosion. Right, so this is the double detonation scenario that we and others are modeling these days. Now that is kind of a convoluted scenario, right? You have two explosions. You don't just have one explosion, you have two explosions, and you're using the energy from one explosion to set off another explosion. But it does have terrestrial analogs. So the obvious one has to do with, well, nuclear fusion. So just across the bay, there's what's known as the National Ignition Facility in Livermore, where they're taking a whole bunch of lasers and they're converging all that energy into a very small volume. So that volume is just a little capsule that looks like this. And at the center of that capsule is a little pellet of fusionable material. So some enriched nuclear fuel. And when all those lasers shine on this, they impart a lot of energy focused into a very small volume, and that is able to start the fusion of this fusion pellet. Okay, so that's a very direct analogy to the this double detonation mechanism. The double detonation mechanism, it's not lasers that are focusing all the energy, it's the first explosion and the shockwave that it sends in. But the idea is sort of similar. You're putting a lot of energy into a small volume and you set off an explosion that way. Now this has obvious implications for bombs on Earth. So I'm gonna go away from this because that's not my favorite topic. This is way more interesting to me. Okay, so this is what's known as a snapping shrimp. These are something like 1 or 2 inches long. They live on the floor of the ocean. One of the claws is very normal. The other one, as you can see, is huge, okay? But it's not that they're using that huge claw to attack their prey directly. They're not, smashing their fish food with this claw. What they're doing is way more interesting. So this is a zoom in of that claw. One part of it's sort of normal. The bottom part has this weird appendage. Okay, when this claw snaps shut, that appendage goes into a slot and it squeezes a whole bunch of water out. So let's see what that looks like. It squeezes a whole bunch of water out really fast. Okay, and it turns out that it's fast enough that the water jet that it's squeezing out at the bottom of the ocean turns into water vapor. There's enough energy in the water stream to turn into vapor. So you basically have steam at the bottom of the ocean. Okay, there's a little bubble, but bubbles aren't gonna last at the bottom of the ocean. There's so much pressure. And so all that pressure refocuses the bubble and collapses it down, and it converges a lot of energy into a small volume. So that collapse actually generates a shock wave of its own. Okay, So this is a crazy bit of evolution where it's evolved this giant claw to spit out water that turns into gas, and that gas collapses and generates a shock wave. And it's the shock wave from that collapse that is what it uses to stun its prey. I think that's fascinating because it's a 1 or 2 inch little shrimp. And it turns out that you can hear these shrimp. They make up a big source of noise in the ocean. So when they first were using sonar, they heard all this noise, and it turned out to be these little shrimp. There's a really interesting Radiolab podcast about snapping shrimp, which I highly encourage you to listen to if you haven't. All right, so that was quite a tangent, but the basic idea is there, right? You converge a lot of energy into a small volume, and you can get an interesting outcome. In this case, it's a shock. In the case over here, it's the fusion of this little nuclear pellet. In the case of the supernovae, the supernova mechanism, it's the initiation of a core detonation, right? Yeah. Okay, so that is a terrestrial analogs. So it does sound like a convoluted scenario, but it actually happens here on Earth, and we think it happens out there in space as well. Okay, so here it's happening in this simulation. You can't really see the shockwave that's being sent into the core, but it is, and that's what is setting off this explosion here. Okay. Now, this is at least my colleagues' favored way of exploding a white dwarf and making a type 1a supernova, but it's definitely not the only way that's been proposed to explode a white dwarf. So there are other ways that I don't have time to get into, but what is it that sets this scenario apart? As I said before, if you take a white dwarf and you blow it up, you're going to make something that looks roughly like a type 1a supernova. And so these competing models have thought of ways to blow up the white dwarf, but what is it, how are we gonna be able to tell which is the successful model, which is the actual way it happens in nature? Well, this scenario has some really interesting outcomes, implications. One of them we can see directly in the simulation. Okay, so remember, this was the explosion. This white dwarf is destroyed, but this other white dwarf it's still there. And it's not clear that this white dwarf will also get destroyed. Right? In fact, in the simulations that we run, it doesn't. What that means is we'll have a survivor from this explosion that's right next to the exploding white dwarf. That's interesting because this explosion is going to, as I said, spread thermonuclear ash all throughout the galaxy in these directions, right? It's converting the carbon and oxygen into silicon and sulfur and iron, et cetera. In this direction, it's going to spew all its ash on top of this white dwarf. So if this white dwarf does survive, it'll have a really unique chemical signature on top of it. We can use spectra, like I talked about before, and look for these absorption features from these interesting elements on its surface. Right? And so we can use that thermonuclear ash on the surface as sort of a chemical fingerprint to tell us that, yes, indeed, this star used to live right next to another white dwarf that exploded. We can tell because of the interesting chemical composition on its surface. And so if we think of the surviving white dwarf as this cake pop, the thermonuclear ash on top is the sprinkles. And these sprinkles are very unique. As I said, again, there's silicon and sulfur, et cetera. These are not things that we typically expect to dominate the atmospheres of stars. Right? Most stars are lots of hydrogen and helium. We don't expect them to have no hydrogen, no helium, and only these weird elements on top. Okay, so if we can find these stars, we can take spectra of them, we can look at their surfaces. If we see this unique signature, that'll be a pretty good sign that what we saw used to be what was right next to a type 1a supernova. How do we find these stars though? And we can't just take spectra of all the stars in the universe. That would be very expensive and take a long time. But luckily, this scenario makes a really unique prediction for helping us find which stars to look at. So again, these are two white dwarfs initially that are in a tight orbit. What's gonna happen when one of these stars explodes? Well, there's nothing holding the surviving star to the system anymore. Right? The reason that these things are in orbit around each other is because of the gravitational attraction between the two stars. When one star explodes and disappears, the other surviving star is just gonna fly away, right? It's just like a sling. So we all know the story of David and Goliath. The weapon that David uses is a sling. We don't see them much anymore. But a sling is basically, well, it's a rock held in a piece of fabric that David is whipping around his head, and when he lets go, the rock goes flying, right? And so you can see the analogy. David here is the exploding white dwarf, and when he lets go, this rock is going to go flying away. In the case of this scenario, this surviving companion actually gets going really, really fast. So something like 2,500 kilometers a second. For us Americans, at 6 million miles an hour. And that's way, way faster than normal stars. So normal stars like the sun and most of the stars around us, they're moving more like tens of kilometers a second, maybe 100 kilometers a second. But this star is moving 10 or 100 times faster than that. So it should be really, really easy to see if we were able to measure the velocities of stars. So the idea would be you find fast stars, you take spectra of them, you look at their surfaces, and if they're covered in thermonuclear ash, you feel pretty good. You say, we have discovered the surviving companions to type 1a supernovae that exploded in this way. Okay, and so that is indeed what we did once we were able to. So in the year 2018, a couple years ago, there was a data release from a satellite that had exactly the kind of information we were looking for. From that, we were able to deduce the velocities of stars. And we took the fastest ones we could that we saw, and we took spectra of them and looked at their surfaces. And what we found, oops, sorry, there's one more thing to say, which is that these stars are moving so fast that they can get to the East Coast really fast, they can get to the moon really fast. Really, really interestingly, they're moving so fast, they're actually ejected from the galaxies that they reside in. So in the Milky Way, for example, a type 1a supernova goes off, and when it does, it can launch its companion star just right out of the Milky Way, right? In fact, it's going so fast that it could ostensibly reach another galaxy in just a few 100 million years, which seems like a long time, but in a cosmic sense, it's actually not that long. So there's the possibility that stars from other galaxies have reached our galaxy and vice versa after having been launched by type 1a supernovae. Okay, so as I said, we were able to look through a data release in 2018 for these very, very fast stars, and we found a few, took spectra of them, and confirmed that they were indeed what we expected to see. And so this is a paper that I wrote with a team in 2018 where we found 3 such stars that I think are the best evidence we have for a type 1a supernova scenario that actually happens in nature. There's no other way to explain these really, really fast stars with their very unique chemical signatures on their surfaces. This was a really fun project to do because normally I write papers with 1 or 2 other people, but here I was working with a team of 30 people, and it was just a lot of fun because, well, for one reason was that this data release was done on European time. It's a European space satellite. And so it happened for us on the West Coast of America at 3 a.m. And so that led to this interesting opening line to this press coverage where I was racing against on blah, blah, blah. It was 3 a.m. and I was sitting at the kitchen table in my pajamas. And I read that today and I was thinking, well, that's basically how I do all my work these days. At any time of day, I am basically at the kitchen table in my pajamas. This was good training for our pandemic life. Okay, so in 2018, we found these 3 stars, and that was great. I felt really good. And I was very confident, I still am, that we have found a type 1a supernova scenario that actually works. It happens in nature. There's no other way to explain these 3 stars. However, I'm not done yet. What I've been working on since then and what I hope to solve in the next few years is whether or not all type 1a supernovae can be explained this way. So we found 3, but what I'd like to have found was a bunch more. And if we had found a bunch more, we would be able to explain all type 1a supernovae with this mechanism. So that's currently what I and other people are working on is trying to understand if this scenario actually happens for all type 1a supernovae. And with that, I will end. Hopefully in a few years, I'll be able to come back and give you another talk and tell you that indeed we have been able to discover all type 1a supernovae come from this mechanism. And that's what we'll be working on for the next few years. And yeah, I'll stop and take questions. Thanks for your attention.